conduction, and we saw the concept of thermal resistance and the heat current equation, which is similar to Ohm's law, that heat current is equal to temperature difference divided by thermal resistance. And we saw that if we have isotropic conductors of uniform cross section, then thermal resistance can be written very easily as L upon Ke. And for combination of conductors, we can use the series parallel methods that we've done in current electricity earlier. But we also saw that if we have a situation where conductivity K is variable because it is an anisotropic material, or the area of cross section is variable, like that funnel shaped object we saw, in that case we have to use integration. And the similar kind of applications of integration where you slice an object into differential elements and calculate the integrated sum for the series combination of the sliced objects. So similar techniques that you've seen in integration earlier in center of mass as well as moment of inertia, those kind of techniques start coming into play. So those are the more important aspects of thermal conduction. So we'll discuss a couple of more examples of application of integration, and then we'll move on to the last part of heat transfer, which will be radiation. In between, I'll talk about few general things to do with convection, but really it is radiation which will be the more important part. And with that, we will complete heat and thermodynamics. Okay, so let's begin. So we'll start with few questions where we'll focus on the application of integration once again, and then we'll move on to radiation. In between, after we complete these few examples I'm doing in conduction, we will also discuss the questions in heat and thermodynamics from the common test which has happened. Okay. So today we'll see another type of geometry involved in the application of integration. We have like a metallic shell, but a thick metallic shell, not a very thin one. So this is a thick metallic shell. Spherical shell, that is. So it has an inner radius of A, an outer radius of B, okay, and the thermal conductivity of the metal is K. Okay. So now, for example, if we do something like this, that we keep the inside of it packed with ice at 0 degrees C. So the inside is packed with ice at 0 degrees C. And the surrounding atmospheric temperature is, let us say, 25 degrees C. So we want to find the rate at which, first of all, heat conducts from the outer surface to inside at steady state. And then we also want to calculate the rate at which the ice melts. And we want to calculate the rate at which the ice melts. So for that also, the latent heat of ice we'll be taking as the quantity L is given to us. Okay. And density of ice will also be required, which will take as. So we are given all these quantities: the inner and outer radius, the thermal conductivity of the material, okay, the surface outside temperature, which is 25 degrees C, the inside temperature of the ice, which is 0 degrees C, the latent heat of ice, which we'll take as capital L, the density of ice, which we'll take as rho. So in terms of all these given quantities, we have to calculate these two things: the heat current, delta Q by delta T, and the rate at which the ice melts, delta M by delta T. Mass per unit time, how much mass per unit time of ice melts. So the first thing you have to understand here, that what is the geometry of the heat current or the heat conduction that will be taking place. What kind of geometry is that? So you'll realize that heat is coming from outside to inside, going through that spherical shell. So it will be a radial sort of current. It will be a radially inwards current. So that is the first thing to understand in the question, that the direction of heat flow is radially inwards. So once it's radially inwards, you can understand that we cannot directly calculate the thermal resistance as L upon Ka, because the cross-sectional area through which the heat is flowing is not uniform. So that is where the application of integration comes in. Okay, so the first thing, as I was saying, you'll realize in the question is that the direction of heat conduction or the heat current will flow like this, radially inwards. So that heat current is not encountering a uniform cross-sectional area. At the outermost surface, the cross-sectional area is 4 pi b square. At the innermost, it is 4 pi a square. So there is a radially inwards heat current. Or delta Q by delta T, which will be temperature difference, outside temperature minus the temperature of the ice, divided by some thermal resistance. But in this thermal resistance, the cross-sectional area through which the heat is conducting is variable. And in fact, it is varying from 4 pi b square at the outermost part to 4 pi a square at the innermost part. So therefore, you have to calculate thermal resistance by application of integration. Of definite integration. Okay. So can anybody tell me what kind of differential element I should take for the integration? What should be the shape of the differential element? Anyone can tell?
Ring.
Sorry? Yeah, tell again, Vita. Yes, that's correct, Amog. Okay. But what type of hollow spherical shells? They should be very thin. Okay. So just like for integrating moment of inertia, na, for solid sphere or thick spherical shell, you would slice it into thin shells, placed concentrically one on top of the other, like the layers of an onion. So like that, you have to slice this thick spherical shell into thin shells of thickness dr, one on top of the other, and the heat is cutting across each of these shells one after the other, so they are in series combination. Okay, so that's what we have to do here. So to calculate the thermal resistance, you have to take a differential element. There should be a thin spherical shell. Okay. So once you figure that out, rest you know the techniques of integration. You have done these techniques a couple of times now in moment of inertia as well as center of mass chapter. So you should not find it very difficult anymore. So anyhow, let's look at it. So within this thick shell, okay, of metal, we will now be considering a relatively thin so a thin shell like this, of thickness dr and radius r. And as we go from shell to shell, that radius varies from A to B. So this shell itself has radius r, and it has a differential thickness of dr. Okay. Now remember, the heat is cutting across radially like this. So the heat current, it is encountering a surface area or a cross-sectional area of 4 pi r square, and it is going through a length of dr. Okay. So the differential shell, it has surface area 4 pi r square and thickness dr. So its thermal resistance, this differential shell's thermal resistance, is going to be dr upon Ka, or dr upon 4 pi r square into K. Okay. And all these shells, one after the other, they are in series combination with each other. The current is going through them like this. So the net thermal resistance will be this integration. So this is summation by integration for the series combination of all shells r equal to A, lower limit, to r equal to B, upper limit. Okay. So okay, so it's a very simple integration then at the end. Okay. So now just complete this integration and work out the value of thermal resistance. And using that, we can work out the steady state heat current or the rate of conduction. Yeah, that's correct, Aman. Okay. With the extra minus sign, it will become 1 by E minus 1 by B. Or also write it as B minus A upon 4 pi KAB. Whatever, both of these are correct. So that is a thermal resistance. And once you got the thermal resistance, the rest is you have to just substitute in the formula for thermal current. Heat current, or delta Q by delta T, is going to be temperature difference, that is the temperature of the outside minus the temperature of the ice inside, divided by the thermal resistance. So in this case, that will become 25 into 4 pi KAB divided by B minus A. So it's like a hybrid formula I've got, like the temperature difference is known numerically, the rest is in parameters. Okay. 100 pi KAB divided by B minus A. So if we substitute AB and K in all the SI units, we will get this in watts or in joules per second. So that takes care of the first part, the thermal current. Okay. Now the rest is easy. We have to find the rate of cooling, the rate of melting. So remember this heat delta Q that is coming in the time delta T, what it is doing, it is converted to latent heat. It is not raising the temperature of the part inside, it's only melting the ice. Only when all of the ice would have melted, then the temperature would again start rising from 0 degrees C. So delta Q should be equal to latent heat into delta M, latent heat of fusion of ice into delta M. So that's how we'll convert this to, to the rate of melting. So we'll convert from heat current in joules per second to the rate of melting in grams per second or kgs per second or whatever. Okay, I'll show the question once more. Yes. Jenny and Nikita, I'll take you back to the question once more. So this was the original question. Okay, so we found out this part. Now from this we have to find the rate of melting. So for the second part, delta M is equal to latent heat of ice into, Q divided by latent heat of ice. Because this formula. So that's it. It's very easy. Just substitute this. Okay. So that density was actually extra information. We don't require it. We will require the density if we want to calculate the total time taken for the ice to melt. If I want to calculate the total time taken for the ice to melt, then I need the total mass of ice. So the mass of ice that is present will be equal to density of ice into volume of ice. So that will be rho into 4 by 3 pi a cube. So in that case, I can calculate the total time to melt all of the ice as this divided by the rate of melting. Okay, so this was another example of the application of integration. It's important. Okay. All right, so hope this is clear, both the parts, right? Okay, now let's move on to a different type of application of integration. Now, this is a very sort of classic problem in physics, which is solved in number of books, etc. also, including H.C. Verma. It is the problem of the freezing of a lake. The time taken to freeze a lake or a pond or any such water body. So what happens is in extreme conditions like Siberian conditions, etc., when in winter the environmental temperature is sub-zero and you have a water body like a lake or a pond or something, then its water starts freezing. Unfortunately, the water freezes at a very slow rate comparatively because of a couple of reasons. One is the high amount of latent heat. The other is the poor conductivity of ice itself. And the most important reason is the anomalous expansion itself, which makes sure that the lake freezes from up and not from bottom. Or as the water freezes, the ice is floating on the upper surface. So anyhow, let's first understand the whole problem. So let's say initially we have water, and just for calculation purpose, we are assuming that our lake or pond or whatever is a regular shaped tank. Okay. So this is water tank, an artificial pond or something like that, which has a uniform cross section A and a depth D. So this depth here is D, and this cross sectional area here is A. Okay. Now initially it's all water. There's no ice. So initially, okay, there's no ice. Okay. But now the surrounding temperature, it drops to sub-zero. It becomes, let's say, minus 10 degrees C. Now, if we assume that the surrounding temperature remains constant at -10, now again, that's a bit of a simplification because in real life conditions, the temperature will vary a little bit between night and day and also with other weather conditions, wind, pressure, all these things. Okay, but assuming the surrounding temperature to remain constant over a very long period of time, at T naught equal to -10 degrees C, and assuming at time t equal to 0, okay, ice has just started to form. That means the temperature of the water has come down to 0 degrees C. Okay. Before this, the temperature might have been at larger than 0 degrees C, might have been at higher temperature, okay, because it was summertime. But as winter hits, the temperature first goes to 0 degrees C for all the water. Okay. And after that, the ice starts forming or the water starts freezing. And once, if the situation occurs that the entire lake has frozen, only then the temperature of the ice will come down further below 0 degrees C, like that. Okay. So temperature of the water is just equal to 0 degrees C at that instant, okay, at time t equal to 0. So you want to find the thickness of the ice layer. Let's say x as a function of time. And from that, we want to find out the time taken for n to become equal to 1 meter or roughly 3 feet. So for a 1 meter thick layer of ice to form at the top, okay, how much time it's taking? That is what we have to calculate next. Okay. Now there will be a whole lot of information given that density of ice is 0.9 gram per
There's
cc.
a lot of delay from your side.
Okay. Then latent. Sorry, what happened with that?
So there is a lot of delay from your side.
There's some delay. Okay. There's some. I'll check the internet connection speed and all that, but okay. Just concentrate on the problem for the moment. So latent heat of ice is 80 calories per gram, and also given to us that the thermal conductivity of ice is 2.22, if I remember correctly. I'll just check the value and tell you. Watts per meter Kelvin. Okay. So all this information is given to us. And from this, we have to calculate the numerical value of this, the time taken for the thickness of the ice layer to become 1 meter. Now notice that the area of cross section is not given. Okay. And the depth of the lake is also not given, which means that it will not be required in solving these two parts. Okay, so just try to figure out what are the things we need to solve in this first, then we'll discuss. Okay, let's try to figure this out. So what we have to understand is that when we reach this situation that all the water has uniformly reached 0°C, and therefore it starts to, ice has just about started to form. So that is the situation at t equal to 0. Okay. So just a minute, I'll need the diagram from above, so I'll just make a rough diagram. So I'm just going to concentrate on the water body. Okay. So I'll compare it at 3 different times, t equal to 0, some time after that, and some very short time after that. So at t equal to 0, it was completely water. At t equal to t, suppose we have a certain layer of ice of thickness x at the top, and then at time t plus dt, that thickness of the layer of ice further increases. So here, let's say so this is the water at 0. To illustrate the fact that we have got an ice layer, I'm showing it with a different color. So we've got ice whose thickness is x, whereas initially I did not have any ice. Okay, and at this point of time, people just carry on with this. I'm having some issue with my internet connection. I'll just switch the connection to something else. Right, so let's continue. So now the ice layer has increased in thickness to x plus dx in this amount of time dt, whereas the water layer, its depth has decreased. So in this diagram, it is d minus x. In this diagram, it is further d minus x plus dx. We can just write it as like this. Okay. So remember, the water will exist at 0°C, whereas the temperature outside is minus 10°C. So that is why this is the direction in which heat conducts. This is the heat current. Okay. So at time t, the rate of conduction delta Q by delta T. Now this rate of conduction is happening through what? It is through a layer of ice, okay, which has a thickness of X and cross section of A. Okay. So this cross sectional area A at the bottom of the tank, okay, that's the same as the cross sectional area of that layer of ice. So this layer of ice, if you think of it three-dimensionally like this, its area is A like this thickness is X, and heat is coming out of it like this, because the outside is at a lower temperature and below here is water at 0 degrees. Oh, sorry. Yeah. Outside is at a lower temperature, so heat is coming out like this. Okay. So this heat current or delta Q by delta T will be K of ice into this area divided by this thickness into this temperature difference. Okay, so in this case, it will be 2.25 into whatever area, sorry, 2.22 into whatever area divided by the instantaneous thickness X into this temperature difference. Should be the other way around. The outside temperature is lower than the water temperature. So delta Q by delta T is, I'll put the value back, but K A by X into 10. Okay. This is our first equation. Okay, now the other thing that is happening is going from T equal to T to T plus dt. Okay. The ice layer has grown in thickness to X plus dx. So how much ice has got formed? No, it will be 0 degrees, Nikita. The water will exist at 0 degrees C. See what is happening. Initially, let's say the water was at 10 degrees C or something like this, and suddenly the temperature of the surrounding atmosphere dropped to -10. So heat will simply radiate from the surface till the water's temperature inside, and inside in the water, convection currents and all will be set up so that the heat keeps circulating and the water uniformly reduces in temperature. But it will reduce all the way to 0 before ice starts forming. So that's why 4 doesn't come in the picture. 4 degrees C to 0 degrees C, there is anomalous expansion, but that anomalous expansion does not involve formation of ice. Formation of ice happens when it reaches 0 degrees C, and then further the crystallization happens, which is what we call the freezing. Okay, so hope this point is clear. Okay, so now going from T to T plus dt, this thickness has grown by this much. So how much ice has formed? So the amount of ice formed or the amount of water frozen, that will be density of ice into volume of ice formed. Okay, so that will be nothing but density of ice into that same area into thickness, because that much part of water has frozen into ice. The ice layer is increased in volume. This is the increase in volume of the ice layer. Okay, so now to form this ice of dm, the heat exchange dq is equal to this mass into latent heat of ice. So the heat exchanged in time dt is equal to density of ice into area into dx multiplied by latent heat of ice. So this becomes our second equation. Okay. Now we connect the first and second equation. Okay. So dq should be equal to heat current into dt. Okay, because heat current only is equal to delta q by delta t or dq by dt. Okay, which is uniform at steady state, uniform and constant. Okay. So this dq is equal to this heat current into the temperature difference into dt. So now connect this with this. So dq is equal to dm into latent heat of ice and further dm depends on dx. So it is density of ice into A dx into latent heat of ice is equal to Ka by x into temperature difference into dt. So everything else is constant, and you see you'll get a relation in x and time, and that relation will be like this. The area will cancel off. This temperature difference is constant. So this whole thing is a constant into dt. So you can see that x dx is equal to some constant into dt, where this constant is K upon density into latent heat into temperature difference. So let's work out the value of that constant. 2.22 into temperature difference was 10. Density of ice will take as 900 kg per meter cube, and latent heat will take an SI unit as 80 into 4.2 into 10 raised power 3. Okay, so that's the value of this constant. And this is the equation we will then integrate to find x as a function of time. And from that, we can answer the second part, that how much time it takes for the ice layer to form 1 meter in thickness. Okay. So again, this application of integration is critical over here. Just go through it once carefully. You see that it takes a lot of time for 1 meter of ice layer to be forming. Yeah, assuming that the temperature consistently remains sub-zero. Okay, so here we are just substituting density of ice 0.9 gram per cc in SI unit as 900 kg per meter. Okay. And we are substituting latent heat of ice from 80 calories per gram to 80 into 4.2, that makes it joules, and into 10 raised power 3, it makes it joules per kg. So we are substituting both in SI unit over here. Okay. Okay. So anyway, this equation that we get, it will tell us that x is equal to this particular constant into dt. Okay, and this constant is this value, which I'll just give you. So x is going from 0 to x, let's say in time 0 to t. We get x square by 2 is equal to this particular constant into time, or x as a function of time will become square root of 2 into this constant into time t. Now this constant is equal to like this. Okay. So this is this equation, okay, x as a function of time. And more importantly, x is equal to 1 meter at t equal to this. So these many seconds, okay. So that is the same thing as divide these many seconds by 3600, you will get it in hours, and divide that further by 24. So you'll see you get something like 78.84 days. So this is the time taken for 1 meter layer of ice to be formed. So you can see it is a combination of the various interesting physical properties of H2O. it's anomalous expansion, which means that the ice floats on top. Okay. The fact that ice is a poor conductor of heat, its thermal conductivity is only about 2.22. So very poor, for example, compared to metals, whose thermal conductivity is of the order of magnitudes of 100 watts per meter Kelvin. And also the fact that the latent heat of ice is very large. No, comparatively latent heat is large. So a lot of heat needs to be conducted out for a small amount of ice to be formed by freezing. Okay, so this is a different type of application of integration in heat conduction. So anyway, with this, you can complete the questions in HC Verma and your module to do with heat conduction, including the applications of integrations. You will find that most of the type of questions we've done in class. So you should not have any difficulty with solving those questions. Now let's move on to the last part of this chapter, which is to do with radiation. But before radiation, in between, we'll just discuss a little bit about conduction, about convection, which is the second mode of heat transfer. Convection is the primary mode of heat transfer in fluids. Conduction was for solids, convection is for fluids. Okay. And this involves by the mechanism of convection currents. Okay. So convection currents are formed due to molecules at different translational kinetic energies. Within the same fluid. Okay. Redistributing heat within the fluid by collisions. So basically you have a container with some fluid in it. Now if you supply some heat from this end, so there is a heat source here, let's say. So what happens is that the liquid molecules here, they gain more kinetic energy. Okay. And suppose the environmental temperature is lower, so there is a heat loss happening from here. So these molecules are comparatively moving with lesser kinetic energy. So immediately this difference in the average kinetic energy of molecules here and here, the translational kinetic energy, sets up convection currents like this. The more active molecules start moving in this direction, and the ones having lower kinetic energy and more passive start coming back here. And through this circulation of actual physical particles, but of different kinetic energies, there's this redistribution of heat. And that redistribution of heat is what we call the convection currents, or it is because of what we call the convection currents. And that is the process of convection. But the whole point here is that the convection currents are highly unpredictable. Okay. And they are not so simple to quantify by equations. Okay, so the process of convection currents are more complex in terms of their behavior with respect to all parameters of the system. So the net result is they cannot be described by any simple equations. Like the equation for heat conduction, you cannot write any simple equations like this, but rather require more complex computational modeling. Something like simulation based on software, that kind of thing. So it becomes a topic in engineering. Cannot deal with it at this level. Part of something called computational fluid dynamics. So all that becomes outside the scope of our syllabus. Okay. So all this becomes beyond our 10+2 syllabus. So that is why nothing really about convection is going to be asked in competitive exams. Just you should have a general idea of what is convection. It is the redistribution of heat within a fluid material where there is a heat source at one end and a heat sink at the other end. And that redistribution of heat happens because of these convection currents that are set up. The convection currents are basically different sets of liquid molecules having different average translational kinetic energy, how they tend to redistribute the heat by collisions between each other. So that process is called convection. And because it is considerably more complex compared to conduction or radiation, we will not be studying it further over here. You actually require to do software-based computer simulation or computational modeling of it. However, it's an important part of mechanical engineering, structural engineering, etc. So CFD is, a part of sub-branch of engineering which is studied by various different disciplines of engineering, including mechanical engineering and material sciences, automobile engineering, etc. Various different subjects. Aerospace engineering also. Aeronautical and aerospace engineering. They do considerable work in CFD. Okay, now the third and the final mode of heat transfer, which we will discuss about in detail, is radiation. So radiation is all about heat transfer by emission/absorption of electromagnetic waves. Okay. Including visible light, infrared, ultraviolet, etc. Microwaves. Visible light has wavelength of about 600 to 800, sorry, 400 to 800 nanometers or so. Infrared, ultraviolet, microwaves. That's it. So basically what happens is atoms and molecules of matter are constantly undergoing transitions. Energy transitions. Like you studied in Bohr's model of atom. So when they undergo higher to lower energy transition, they tend to emit photons. Or electromagnetic radiation. When they tend to undergo lower to higher energy state, this occurs because of photon absorption. An atom or a molecule will absorb a photon to go from a lower to transition from a lower energy state to a higher energy state. Similarly, it will emit a photon to undergo transition from higher energy state to lower energy state. Now, these transitions are constantly happening all the time, driven by probabilistic factors. Okay? So such transitions always continuously take place in matter. Due to probabilistic nature of atomic or molecular quantum mechanics. So as you study more in science and technology, you might be able to learn more about quantum mechanics in future. In future parts of your study. Not much about quantum mechanics will be studied over here at 10+2 level. We will discuss a little bit about quantization of angular momentum and Bohr's model of atom and all that in the last section of physics, which is based on which is called modern physics. Okay. But again, here it's not going to be of concern to us directly. This is just the the background reason why radiation happens. Now, the actual qualitative description of radiation will not involve any probabilistic quantum mechanics and all that, but just the reason why radiation happens, why emission and absorption happens, is because that's the way atoms and molecules behave. They're always randomly in a process of continuous absorption as well as emission of photons, because they are continuously undergoing these transitions in a random sort of manner. And that randomness is driven by that probabilistic nature of quantum mechanics. That if so many outcomes are possible for a given cluster of atoms or molecules, then there is a sort of distribution of probability that which particular outcomes will happen at which point of time. And that is basically the essence of wave nature of matter. No, so Aman, to answer your question, yeah, and Kevin, I'll scroll up in just a bit. Aman, to answer your question, that heat transfer happens by radiation. So the moment we're talking about radiation, we're talking about emission or absorption of waves which are in the electromagnetic spectrum only. The term radiation itself means electromagnetic waves. So that has to be part of the electromagnetic spectrum. It cannot be, I mean, it's not any other type of wave. No? So anything which is electromagnetic in nature, in wave nature, it is part of the electromagnetic spectrum, right from radio waves to gamma radiation. Any electromagnetic phenomena, electromagnetic wave phenomena is somewhere in that electromagnetic spectrum, from highest wavelength, which is of radio waves, to the lowest wavelength on the other side, which is of gamma radiation. Okay, so when we talk about radiation and heat transfer, we're talking about radiation via electromagnetic waves only. So it has to be, so now you understood. The waves emitted or absorbed have to be somewhere in that spectrum of electromagnetic waves. And typically they are in a more specific part of the spectrum which is around the infrared, ultraviolet, visible light, that region. For that matter, even X-rays will create heat transmission, but the predominant heat transmission that happens for most materials near about room temperature is through the part that I told you, between visible light and infrared and ultraviolet. Kevin, this is the part you wanted to go through once more. Okay. Okay, so now we come to the mathematical principle that is derived basically from experimental observation about this continuous emission and absorption. And this is given by Stephen's law of radiation. So this is again an experimental law. There's no derivation of this. This is how matter behaves, but behaves with respect to electromagnetic radiation. Whereas, for example, the law of thermal conduction was again an empirical or an experimentally determined law, which we understood from the behavior of matter with regard to conduction. So basically behavior of typical solid materials when they are put under a temperature gradient. We observe those experimentally and put forward those principles which tell you about the heat conduction being proportional to temperature difference and inversely proportional to thermal resistance. Now, like that, if we experimentally observe radiation from surfaces of various different bodies made of various different materials, then that empirical data will point us to certain mathematical facts. And that is what Stephen's law is about. So if we have a surface, okay, at a temperature of capital T, which is the temperature in kelvins, then Stephen's law suggests that the emissive power E. Now, what is emissive power? Let's understand. It is the rate of energy radiated, or you can say emitted, that is by electromagnetic radiation, or basically by just releasing photons. So rate of energy emitted per unit time, per unit surface area. Okay, that emissive power is proportional to the absolute temperature to the power 4. So this is the logical part of the Stephen's law statement. I mean the conceptual part, that emissive power, how it depends on the surface temperature. It depends on the absolute temperature of the surface raised to the power 4. So first of all, there's a definition over here that what is emissive power. Emissive power is defined as the energy radiated per unit time per unit surface area. So emissive power is expressed in watts, that is energy per unit time per meter square, or joules per second per meter square. That is the SI unit of emissive power. So it so happens when we observe various different materials experimentally at various different temperatures, the empirical data leads us to conclusion that emissive power of a surface, that is a unit surface area, is emitting how much energy per unit time. That depends on the surface temperature raised power 4. Okay. Now let's come to the constant of proportionality for this proportionality symbol. Okay, so such that the value of emissive power is given by a constant called emissivity multiplied by another universal constant called Stephen-Boltzmann constant, or simply Stephen's constant, into temperature to the power 4. Okay, but remember the temperature has to be expressed in kelvins. It's absolute temperature, where here sigma is Stephen's constant of radiation, or we also call it Stephen's radiation constant, which is a universal constant. It does not depend on anything else. Okay. Sigma is experimentally determined to be 5.67 into 10 raised power minus 8 watts per meter square Kelvin to the power 4. Okay. And E, small e, is called emissivity. It is a material property of the body. Okay. Now E is a unitless or dimensionless term, which is less than 1. Greater than 0, but less than 1. Okay, so this is the statement of Stephen's-Boltzmann law. See, there is a material property involved now, which is the emissivity. So we are assuming that the surface is made of isotropic material, because otherwise the material property cannot be determined as a constant. So if it's a mixture of different materials at different percentages, then emissivity will not be uniform. But anyway, it's per unit surface area, na? So it's at a particular point. So really does not matter when we express it in terms of per unit surface area, when we express it, whether it's isotropic or not. It just means that at that particular point where we are calculating emissivity or emissive power, the material has a certain value of small e, which is the emissivity. Okay, so the name is a little bit misleading, that power is generally expressed in watts, but this is more like intensity actually, which is power per unit area. But we don't call it intensity, instead we call it emissive power. Okay, so just make a note of this, then I'll explain in more detail what is emissivity. Okay, so now let's talk about emissivity. So emissivity is actually a factor which compares different materials according to how well they emit. Okay, so emissivity is a material property. Okay, it is basically a fractional value. Like emissivity might be 0.5, emissivity might be 0.2, emissivity might be 0.9, etc. So it's just a simple fraction or a value less than 1 to compare the emissive power of different materials. Okay. Now you'll understand that whenever we do a comparison, we have to do the comparison with respect to some absolute. So the absolute that we consider over here is, you might have heard this term, it is called a black body. So a black body is a theoretical material which has the absolute maximum emissive power. So it is just defined theoretically as a material whose emissivity is equal to 1. So then you can say that emissivity of any actual material is equal to the emissive power of that material divided by the emissive power of a theoretical black body at a common temperature. So if you take a black body at a temperature T and you take whatever actual material I have, but again at that temperature T, then this one will have an emissive power of sigma into T raised power 4, because this is a black body. So its emissivity is 1. And this one will have E into sigma into T raised power 4, because this is some actual material, not a theoretical black body. That's how you can see that we can define emissivity of a material as the comparison of the emissive power of that material with respect to the hypothetical black body if you keep them at the same temperature. So the black body is like the perfect emitter of heat. So how much that will emit per unit time, per unit area, in comparison to how much our given material will emit at the same temperature. So that ratio is nothing but the emissivity, or small e. And that's why it's dimensionless. Right. So that is the definition of emissivity. So the rate at which a material is emitting from its surface per unit surface area depends on two things: the material itself, which is the emissivity, and the temperature of the surface in absolute scale, capital T.
So is there a set method to calculate emissivity?
Whereas sigma over here, Stephen's constant is a universal constant. Okay. You don't need to memorize the value of sigma. Just it will be given to you in the question paper with the other constants. Okay, now the other part about radiation which we are discussing is that while any material is constantly emitting, it is also constantly absorbing. So if the surrounding temperature, the surrounding environment in which it is, that temperature is T0, okay, whereas the surface temperature we had seen was T. But now we are more interested in the surrounding temperature, T0, in Kelvin. Then the material also has something called an absorptive power. Like an emissive power, it also has an absorptive power, which is energy absorbed per unit time per unit area by its surface. So again, absorptive power is also in watts per meter square or joules per meter square second, whatever. So now absorptive power, as it turns out, is proportional to temperature of the surrounding to the power 4. And again, that constant is a material factor called absorptivity into the same universal factor, universal constant, Stephen's constant, into the absolute temperature to the power 4. So T0 should be in kelvins. Sigma is the same thing as in the formula of emissive power. It is Stephen's constant of radiation and given by that value. Kelvin to the power 4, okay. And E over here is absorptivity. So again, it is a material factor or a material property. And it is a dimensionless term. Less than 1 for any actual material. Now, when we put these two, phenomena together, that any material kept in a sort of environment which is at some temperature T naught, and the surface, so let's say this has surface area equal to S, okay, S in meters square or whatever. That's the surface area, and it's a material with emissivity equal to E and absorptivity equal to A, and it is at a temperature, at a surface temperature of capital T in kelvins. And this material has been kept, or this body has been kept in an environment which has a temperature T naught in kelvins. So this is the surrounding temperature. So in this situation, which is basically the situation in which any body will find itself, continuously the process of emission as well as the process of absorption is taking place simultaneously. So emission and absorption simultaneously occur continuously. So as they occur, what happens is that the rate of emission, that is, we can say dq by dt, will be nothing but emissive power multiplied by surface area. So it will be E sigma into that surface area into T to the power 4. Whereas the rate of absorption dq by dt, or you can even write it as delta q by delta t, but absorption will be absorptive power multiplied by the same surface area. So it is A into sigma into S into temperature of the surrounding to the power 4. Okay, so this is in watts or joule per second. Same thing here, it's in watts or joule per second. So now what we'll understand that logically, if the temperature of the surface is equal to the temperature of the surrounding, it should be in thermal equilibrium. That means the net heat exchange should be 0. So now this is a little bit more complex here, because net heat exchange is 0, but at the same time emission and absorption are continuously taking place. So if net exchange is 0, that means the emission is exactly balanced by absorption, because emission causes the body to lose heat, absorption causes it to gain heat, but the net heat exchange is 0 because the body is in thermal equilibrium with the surrounding. So that can only happen if the rate of emission is exactly balanced by the rate of absorption. Okay? So that's the first condition we'll see that occurs for radiation. Okay. So if the temperature of the surface is identical to the temperature of the surrounding, it implies that the body will be in thermal equilibrium with its surrounding. That further means that the net heat exchange, they should be 0. Now the net heat exchange is nothing but the rate of absorption minus the rate of emission. So this must be equal to 0, but under what condition? Under the condition that the temperature of the surface is equal to the temperature of the surrounding. Okay, so we will look at these two equations from above in this condition over here, and from that we will come to another important conclusion about absorptivity and emissivity, which is coming up next. So just note down up to here, people. Okay, so now when we put this further, we can see that emissivity, sorry, left hand side we have absorption. So absorptivity into Stephen's constant into surface area into temperature of the surrounding to the power 4. That is the net rate of absorption will exactly balance the net rate of emission, which is E sigma S into temperature of the surface to the power 4, provided okay, that temperature of the surrounding is equal to T. So that means for any material, the absorptivity is equal to the emissivity. They're defined in different ways, but they have exactly the same numerical value. So this is a property of all materials. Okay. So for any material, the value of emissivity equals to the value of absorptivity. Okay. So that also shows that for a black body, emissivity is equal to absorptivity is equal to 1. And for any material, absorptivity equals to absorptive power of that material divided by absorptive power of black body. And emissivity equals to emissive power of that material divided by emissive power of black body. And for any real material, the value will be less than 1, but it will be a common value. So something which is comparatively a good emitter will also be a good absorber. Similarly, anything which is comparatively a poor emitter will also be a poor absorber of heat. So there are materials like lamp black, which is a certain form of carbon, which have very, very high emissivities or absorptivities in the region of close to 0.98, etc. So certain materials you can say can be approximated as perfect black body materials. But the concept of black body is it's a hypothetical material. It's a theoretical state of matter which has the absolute value of emissive power. That is sigma into T to the power 4. So its emissivity is 1. Okay, so once we are through with these principles, then we'll see that there are certain types of numerical problems related to radiation also, which we have to learn to solve. Now, having understood this, next thing we'll see that if the temperature of the surface is greater than the temperature of the surrounding, okay, for a given body, then it loses heat. The heat exchange is in such a way that it loses heat and its temperature starts dropping. It tend to lose heat by radiation. And the net rate of heat loss is a minus dq by dt. The minus sign showing that its own there is a net rate of heat loss and its heat content is reducing will be equal to the rate at which it's emitting minus the rate at which it's absorbing. So that will be nothing but emissive power multiplied by its surface area minus absorptive power multiplied by its surface area. So this will become E sigma into surface area into T to the power 4 minus this will become absorptivity into sigma into same surface area but into surrounding temperature to the power 4. So that same situation, it has a surface area equal to S, temperature equal to T, and emissivity and absorptivity. Now we know E is equal to A, be less than 1 of course, and the surrounding temperature is T naught. So this is the net rate of heat loss. Okay. Now further here you can see that E is equal to A. So the net rate of heat loss in fact is given by this kind of an equation. You can take E equal to A common. So temperature of the surface to the power 4 minus temperature of the surrounding to the power 4. Okay, if you're familiar with Newton's law of cooling, which you might have done as an experimental thing in class 10th, I don't know, you might think initially that this contradicts Newton's law of cooling, but I'll show you that it does not. Newton's law of cooling is like a further special case of this when the temperature difference of the body with respect to the surrounding is not too large. So this approximates or reduces to Newton's law of cooling in that case. If you haven't seen Newton's law of cooling, it doesn't matter. We'll be discussing very soon. Okay. Whereas on the other hand, you can also see that if the temperature of the surface is less than the temperature of the surrounding, then the body tends to gain heat because the absorption will dominate over the emission. So in that case, plus dq by dt net will be equal to absorption into surface area, absorptive power into surface area, minus emissive power into surface area. Okay. So again, it will become this minus. So it's just basically the reverse of this because now T naught is becoming greater than T. So and you can always replace E with A also, small e with small a because they are same. So they're interchangeable. So this is the situation that occurs if the surrounding temperature is greater than the surface temperature. This is the situation that occurs if the surface temperature is greater than the surrounding temperature. And remember always to substitute temperatures in kelvins. Okay, so for example, we have a situation like this. We have, let's say, a solid cube whose surface temperature is known to us and whose dimensions are known to us. The solid cube of dimension L by L by L, where let's say L is 2 meter, at surface temperature T equal to, let's say it's given to us in degree C, we'll convert it to later, okay, of material of emissivity equal to 0.6, okay, in an environment of temperature T naught equal to 27 degrees C. You want to calculate emissive power, absorptive power, and the net rate of heat loss. So, want to calculate all these things. So, emissive power will become E sigma into T to the power 4. So, here that will be 0.6 into 5.67 into 10 raised to minus 8 into, now see, this will have to convert. So, this will become 400 Kelvin. So, this factor you can see will take care of itself. Okay. So, you're left with 0.6 into 5.67 into 16 squares, that is 256. So, this much in joules per second. Okay. So, this will be per meter square. So, this will be the emissive power. Similarly, absorptive power will be A sigma into T naught raised power 4. So, remember, A will be equal to E. So, it will be 0.6 again into 5.67 into 10 raised power minus 8. That is our Stephen's constant. This is sigma. Okay. Into T naught. Now, T naught we will convert, and that will be 300 Kelvin. So, 300 to the power 4. So, absorptive power will become 0.6 into 5.67 into 3 to the power 4. That is the same thing as 9 square, so that's 81. Joules per second per meter square, or watts per meter square. Okay. And likewise, now the net rate of heat loss will become, okay, or E sigma S into T raised power 4 minus T naught raised power. Now the surface area S over here will be 6 times L square. So 6 into square. So 24 meters square. Okay. So we substitute that. Sorry, there's a factor of 10 raised power minus 8 here also. Okay. Stephen's constant. Now this we can write as 256 minus 81, taking 100 to the power 4 common. So 256 minus 81 will give us 175 into 10 raised power minus 8 into 100 to the power 4. So this factor cancels out and this is the value we get. This time it's in watts or joule per second. So this is the net rate of heat loss. All right, so this type of calculation you have to be able to do in this chapter, and we will see that there are some questions where you might have to combine concepts where in the same system there is a combination of things happening like radiation and conduction, etc. And some kind of steady state analysis has to be done. So that and more coming up in the next lecture, and with that we will conclude heat and thermodynamics. Okay, so that's it for today's session. People, wish you all the best. Yes, I will take the comment as doubts from heat and thermodynamics in the next lecture. Someone.